Okay, so what we're going to do then is take a look now in this part about the finite element solution for a center cracked plate, the biaxially loaded plate. Here we have 100 megapascals applied on each side away from the crack. We have a 20 millimeter crack, and we're going to do quarter symmetry. We're going to use Newton millimeter system and use properties of steel. Here we have rollers applied ahead of the crack tip that restricts deformation in the y direction. We're going to have rollers applied all the way up here on this left side that restricts any motion in the x direction. Those are going to be our symmetry boundary conditions. And just to highlight it here, there's no boundary conditions on the other than this one on the left side on the crack faces. Okay. And so we're going to set up our finite element model. We're going to bring up our ABAQUS, bring it over here, and we're going to create a new part. Drop down over here. It's going to be a 2D deformable shell feature with 200 size, and we're just going to key in those particular points. So 0, 0, 0, 10, that's the start of the crack tip. Oops, 10, 0 rather. 100, 0, 100, 100, 0, 100, and I'm going to get rid of this point right here. So I put that in extra. So let's resize this. Now we can see the outline of what we have going on here. We're going to use a connect the points option, and we're just going to go around this and hit all these points pretty quick. Since we've used ABAQUS quite a bit now, I'm going to go a little bit faster through some of this. Alright, we're done. I'm drop down to property, mechanical, elasticity, elastic, 210,000, and 0.3. I'm going to make a section, and this is where I always kind of have to do this over sometimes. What we need to select here is a solid section, a homogeneous solid. It's a little counterintuitive to me since we're using shell elements. We're going to use a shell element, but we're going to do a solid in this category. And we're going to use material 1, and we're going to use a plane stress thickness of 1. Now we're going to assign our section individually. We're just going to make a big box around this object. And here it is. If we had chosen the wrong thing, if we had chosen shell by accident, we would not have a section that would show up in this list. Right, and there we have it. Alright, so we're done with our property. We're going to come down here to assembly. We're going to instance the part, just like that. We're going to go into step. We want an initial step with some boundary conditions, and then we want to create a new step with some loads with static general. And time period of 1 is fine. We won't worry about nonlinear geometry. Okay. Interactions, we don't have any. We'll go into loads, boundary conditions. But see, step 1 is the active step right now. Let's go into initial. And I'll right click on the boundary conditions and create a boundary condition on displacement and rotation. And I'm going to do this left edge. And like we talked about, we don't want any displacement in the x direction on that left edge. I'm going to create another one on displacement. And I see how it's only highlighting this area that is ahead of the crack tip. See, our crack tip stops there. Kind of that coordinate system kind of gets in the way a little bit. Guess it's going to scale with it. All right, so we just want to select that edge. And on this one, we do not want any displacement in the y direction. We're going to go into step 1, and let's make a load in step 1. Pressure load. And I'm going to select this top edge, and since we need to do biaxial, I'm going to press shift and select the right edge. We want it to be in tension, so we have -100. and there's our stresses, our pressure. Let's see, let's do one other thing while we're here. Let's create a set. That was one of the things that we wanted to do. Let's do it in the assembly. I'm going to right click on sets and hit create, and I'm going to create a set, and I want this to be on geometry. I'll talk about what that means in a moment. But I'm going to name this set B nodes for bottom nodes. And so we're going to make a set of all the nodes that are on this geometry line. When we mesh our part, if we remesh it, since the set is associated with the geometry, any nodes in the remesh will be included in this node set that lie on this bottom line. If we did not do this based on geometry, we would have to reselect the nodes every time we remeshed. So it's just kind of depends on what you want to do for this. But we'll do this on geometry. Alright, so we made our set. Now I guess we need to get into the mesh. We'll drop down to that. We're going to seed our part instance. Now this thing pops up. Dependent part instances cannot be edited or assigned mesh attributes. Try the operation on the associated part or select make independent from the model tree. What we want to do in this case is we want to change this over to part up here and select this as part 1 and then do our mesh seed. Now we're going to use a fairly fine mesh. I'm going to put in 0.25 millimeters. This is very fine. You can back this off if you find this takes longer than what you have time for with your computer. It's also possible to do a graded mesh, as we talked about, selective mesh refinement near the crack tip. But for purposes of getting through this part of the analysis quickly, I'm just going to use a uniform 0.25. And then I'm going to mesh the part. Okay, so you see it's an extremely fine mesh. Alright, I think we are almost done. So I'm going to make a job. I think I've got everything. If I haven't, we'll figure it out soon enough. I'm going to create a job, and it's going to come off this one, center cracked plate, and I'm going to make this base input. And hit continue and hit OK. Now I'm going to come down here and I'm going to right click on this and I'm going to write the input file. I'm not going to do a submit. I'm going to write the input file. You see it's written it as base input.inp. I'm going to find that and I'm going to open it up. Here it is. I've got my Crimson editor that we're going to open that up. It's a fairly large file, so it's going to take a moment. So there it is, and there's our node definition. It's based on parts. And down here at some point you'll find the assembly. There's our element definitions. But what we're really interested in is we're going to come in here and take a look in this. The interesting stuff kind of happens at the end. This is our step, the initial boundary conditions here, and here's our step 1. And we can look up in the keywords manual what star static means and all these different things. Basically, we have a unit time and so forth. And we have a surface load on the defined surface surf-1, a pressure load that's minus 100. And here are the output requests. Oh, we need to do one other thing. We made the set, but we need to include a field output request for the set. So let's go back into CAE. And we'll get into step 1 and we're going to do an additional field output request. F output 2, and we're going to do, instead of the whole model, we're going to do a set, and we're going to do the set for just the bottom nodes. Now the items that we want, we're going to do S, and we're going to do coordinates. That's under this one, down at the bottom. And I think that's what we need for that. Now you can choose other things. I'm just picking a couple because I want to show you how this works. We may or may not end up using these. Alright, so then we're going to hit OK. And let's rewrite that base input again. I'm not going to submit it, we're just going to hit the right input. We're going to override it. And then when we get into Crimson, it's going to tell us it's been modified and we can reload it. And we'll get down to the end again. Okay, so here's a node output, inset equal b nodes, and it's going to output the coordinates. And now it has an element output for L set b nodes, directions equal yes, and it's going to have S. Now, the deal with nodes and stresses, as we talked about in class, stresses are calculated at integration points and they're extrapolated out to nodes and they're averaged across elements. Okay, so we really can't directly output stresses at nodes from ABAQUS. We can output element stresses and then we can let CAE do the interpolation and the averaging and all of that, and then we can spit those out and take a look at it. Or we can use, and so that's what's going on here. All right, so it also made an element set based on B nodes, as it was on the geometry. Now, we're going to add something else. Suppose we wanted to see some things that we could get based on the nodes. Now, I'm going to open up the manual, and I'm going to come down here, and there's a couple commands that will write things out to the .dat file. One of them is this one, node output, node print. Okay, this option is used to provide tabular printed output of nodal variables, displacements, reaction forces, etc. in the data. And this is history data, and it says output to the data and results files. Okay, so we need to know where it's going to end up, and we need identifiers. So if we want to go back, we can read output to the data and results files. Let's see if I have that called up already. And then here's all the nodal variables. We can look at displacements, translational components, rotations, all these different things, assuming they're all calculated. RF is reaction forces. That's usually a very convenient thing to have out at nodes and all of these. So what we're going to do is we're going to add a couple things just to write out to our .dat file. Alright, so we're going to add a star node print, and we're going to add a star L print. Let me take a look at our input file, and I'll show you what I just added. Okay, so down at the bottom here, I got a node print, inset equal B nodes, reaction forces and coordinates. And here I have an L print, L set equal B nodes. See, now it has this defined for us. Position equal averaged at nodes. And what we're going to do is we're going to write out the stresses. And then we're going to end the step. So we're going to save that. I save that as base input -mod.inp. We're going to go back to our CAE file. I ran it just to make sure it would work, but let me delete this job. Now, since we have modified the input file, we don't want to use this base input. What we're going to do is we're going to come up here and we're going to create a job. Instead of source being model, we're going to use source equal input file, and we're going to select the input file. And we're going to select base input mod.inp. And now we are going to right click on that and submit it. Since I already ran it, it complained about data files already existing, but that's okay. Alright, so it's doing its thing now. It's going to take about 30 seconds or so. Like I said, it's a pretty fine mesh. one thing I will caution you about is the L print can produce a lot of information in that text file. So you want to make sure you're using a good text editor when you load it up. Or there's ways that you can cut down some of that extra junk that's in there. All right, so we'll let this run, and we're going to load up the results here in just a moment. And we'll see first of all what our stress field looks like, and then we're going to take the information from our DAT file and bring it into Excel. All right, so it says it's completed. Let's first take a look at our stress fields. So I'm going to right click and look at results. This thing comes up every once in a while. I don't know why, but safely ignore that. You see the whole thing looks very dark. So I'm going to go up to Options, Common, and I'm just going to do Feature Edges. And this is what our default contours look like. So this is a contour level of 500 right here. Let's go ahead and change our maximums and minimums. Options, contour, minimum 0. Let's make our maximum 500. Okay, so it changes it a little bit. Now let's go to ODB display options under View. We're going to mirror the XZ and the YZ plane. And there we have our center cracked plate stresses. Options, let's see what our deformation scale is. We have a very large deformation scale. Let's change this to 1 and see what that looks like. And if we zoom in on the contours, here you can see that very flat surface, just like we calculated near the cracked tip in our Excel file. Okay, so you see how that takes shape, and it's near the cracked tip. Remember, these are near cracked tip stress fields, so we want to be fairly close. But that shape does look very nice, particularly this kind of darker green shape. Now here you get some resolution issues with the element size and so forth. Let's see what happens if we animate this. Maybe we need to zoom out a little bit. And let's see, let's see what some of these other options look like. That doesn't do much for us. Since we only had one final and initial step, I guess we don't have very good animation. If you wanted to take a little bit more time, you can make 10 steps, and we've shown how to do that. But we can change the maximum contour level. Options, contour, change this to 300. Okay, and we can see that we have traction-free stress surfaces here, and as we get away from the cracked tip, we get into that cracked tip stress field. Alright, so we didn't use anything special. We didn't do any fancy elements or anything like that. All we did was separate nodes in our mesh. Now, there's something that you should be aware of. If you were to accidentally have duplicate nodes and you had nodes separating, you will get a stress contour that looks similar to this. So if you see this kind of stress contour in your finite element plot, then you would expect that you had some separation of nodes going on there. You have a crack-like defect in your model. Whether or not you want that in there, you would have to figure that out. Let's kind of back this off a little bit. Maybe let's see what a level of 50 looks like. So that's showing the crack opening, and if we were to look through this, so there it is closed, there it is open, and so forth. There's this kind of stepwise animation. So you can kind of see it opening and causing those contours. Alright, so that part looks great. Now we're going to do a little bit of work. We're going to look at our DAT file and we're going to bring those into ABAQUS and we're going to compare that to our analytical. We're going to bring that into Excel. We're going to compare that to our analytical solution. Alright, so I'm going to go to my Crimson editor and I'm going to load in the DAT file. And it's going to take, it's a big file, so it's going to take just a little bit of time for that to load in. And there it is. Now, what I'm going to do is, let me get in here somewhere, and I'm going to search for my node set, B nodes. And here's my coordinates. Here's the node number, and there's my, oh, sorry, this is the stresses. Here's my node number, here's my stress 1122, and my shearing stress S12. These are on that set. So what I'm going to do is I'm going to highlight this stuff, and I'm going to paste it in to an Excel file. So let me do something here. Let me create a new sheet. I'm going to go back to this. I'm going to highlight that, and let's go down to here. So I'm going to go between there. I'll scroll up. It's taking a little while. Let's see. Page up. And here. And I'm going to right click and copy, and I'm going to come over to my Excel and I'm going to paste. Oops. Let's use the text import wizard. I don't know what that other junk was. We're going to use the text import wizard, and we're going to do a fixed width and hit next, and it looks like it's pretty good. So let's do finish. Let's see. Didn't seem to like that. Let's try this, something else. Let's create a new sheet. Text import wizard. Let's do delimited with spaces. And for some reason I'm not getting very much data. Let me find out what's going on. Pause it and I'll fix it. Oh, I see. For some reason I only had a little bit of data selected, so let me try this again. Alright, so now I think I have the entire selection. I'm going to use the text import with delimited, space delimited. And now we have all this data. Now remember, our first thing was our node number. This is S11. What we really want is the S22, stress in the Y direction. Here's our S12. And we're going to go back to that data file. And now here's the reaction force and the coordinates. Okay, so we're going to highlight this. I'm pressing shift and page down, or shift and arrow to get all of that. I'm going to edit and copy that. And let's see, we're going to do the same thing. We're going to use text import wizard. We're going to do it delimited with the spaces. Okay, and this is the node. This is reaction force 1, reaction force 2. This is the x coordinate. And these must be elements. So this isn't exactly what we want. We want only the elements, only the nodes that are in this node set. So what I think it's done is it's gone and found some additional nodes that are not on the bottom, but they're in the element set that composed of the nodes on the bottom. So that's not quite what we want. So what we're going to do then is we're going to go back and we're going to use the tool in CAE to come up with the stresses at a few nodes along the bottom. But this is good information though. So this is the node number. We're going to get rid of these reaction force terms. We're going to get rid of this one. I'm just going to delete that. And we'll come up with position and stress value. Okay. But I did want to, even though this didn't quite work out exactly like I thought it would, I did want to point out how you can write data to the node file. Now there's different options in ABAQUS for plotting things. I find plotting with time very easy. I find it kind of difficult to plot two different variables against each other. I know it's possible, but I find it very difficult, so that's why I end up using Excel a lot. So what we're going to do, and this is kind of part of it, but what we're going to do, we're going to go back here. Let's change the ODB view options. We're going to zoom in kind of down here, and we're going to do a tools query node pro values. We're going to select nodes from the viewport, and the field output we're going to do S22, 75% averaging. Alright, now in order to pick the nodes, I'm going to turn the lines back on. And I'm going to zoom in here a little bit more. And I'm going to select a bunch of nodes from the viewport. So right here, you notice they're adding to this table. Now because each node is shared by two elements, we're probably going to get two values of stress. So we're going to have to manipulate this data just a little bit. Remember, each one of these is 1/4 of a millimeter. I want to get enough points that we have a nice looking picture to compare with our analytical solution. So that's probably enough right there. So here we have the original coordinates and the S22 value. I'm going to write this to a file. I'm going to call this ABAQUS dash node stress dash RPT. No limit on page width, and hit OK. And that should write to our temporary directory, this file, and I'm going to bring that into here. Alright, so here's our nodes. Here's our X position. And here is our S22. And like I said, you see how each node is in here twice. Even though the value is the same, each node is in here twice. So what I'm going to do is I'm going to copy this information over into Excel again. Let's do this on a new sheet. Just Control C on that. We'll import it. We'll go back to the text file. Copy this. and paste it in here. Let's see, let me do it down here. All right, and so this is the stress column here. Now what I'm going to do, and I won't do this while I'm recording, it's kind of a toss-up as to how to deal with some of this data. I'm just going to delete the extra points in here. But what you can do is you can write this to a text file and process it with Fortran or Python or whatever you want to do. But what I'm going to do is I'm going to get rid of these duplicate points. So I'll be right back. Alright, so I did that. I copied these over here with their node numbers, and it's a good idea just to make sure the node numbers are matching up. And it looks like they are. So what I really need is I need these x values. And I need these S22 values. And I'm going to go in to my Excel spreadsheet where I did my calculations. And I plotted on here my X value for several millimeters of plate in front of the crack tip. Then I added 10 millimeters to it. And then I calculated sigma y. So I took this sigma y equation and I set theta equal to 0. Of course, this goes to 1, and these two terms go to 0. So I'm plotting k1 over square root 2 pi r. Let's check that formula. Okay, so the blue one's k1 divided by 2 times pi times the r value, which is this cell right here, to the 1/2 power. Okay, now of course I get infinity for this very first point, all right, because we got infinite stresses there. But here it tails down, and as we get ahead of the crack tip, these stresses start to drop. And by the time I'm at 5 millimeters ahead of the crack tip, total x distance from the center of the plate of 15 millimeters, I end up with a stress of 100 megapascals. Now remember, these are near tip crack stress fields. So as we get a little bit away from the crack tip, the analytical solution really doesn't apply. So we may not get exactly the same thing in our finite element results. But let's take a look. So let's see what I've got here. I'm going to take my other spreadsheet values. And I'm going to paste them in. I'd done this earlier, so that's why there's some numbers that are sitting there. I think I have a few more numbers now. Okay, and there I have my plot comparison. Alright, so in the blue dots, that is the analytical solution. Here's the crack tip right at x equal to 10. For the red dots, that's the finite element solution. And you notice our stresses are a little bit higher even out in front of the crack tip. We have a finite width plate, and we use the analytical solution for an infinite plate, and so forth. So there's a little difference there. But you see that it's very nearly following that analytical solution. It's picking up this curve right here. We had to get a ton of elements to pick up that curve. Let's kind of zoom in on this a little bit. See this point right here? That's kind of a spurious point. That doesn't really make any sense, but that's probably the one right at the tip of the crack. Let's change this maximum to maybe 600. Okay, so we can see a little bit more of a difference here. but in general it follows it pretty well near the crack tip. Again, I can't say this often enough, but the analytical solution was for assuming extremely close to the crack tip. So we can use just regular elements to help us pick up a stress intensity factor. What you can do is you can fit this to a 1/r curve, and you can extrapolate this to find the geometry factor or stress intensity factor. But again, I want to point out that we use an extremely fine mesh. The power of the J contour that we're going to take a look at next time is that we'll be able to use an energy measure to relate to the stress intensity factor, either for elastic or elastic plastic material behavior. But that J contour integral will be able to help us capture that singularity without having such level of refinement. Still have to have a very nice, well-refined crack front, but we'll explore some options again with ABAQUS and with a piece of software called FEA crack. Alright, so that's what I'd like for you to do for your homework on, I guess that's number 9, taking a look at crack tip stress fields, analytical comparison, finite element comparison. I will give you this spreadsheet minus the finite element results, and you can do your own, and then you can do some other type of analysis. Maybe you want to put a shear load on it. Maybe you want to do something different. Finite element with just a tensile load. You won't have an analytical solution to compare with very easily unless you look it up, but I think you'll find it kind of interesting. Alright, that's enough for this one.